Share the screen. This one. There we go. What's up, everyone? We got we got 12 learners, 13 learners. Wow, nice. This is my it's my first time here on Lighthall. I mainly do things on Twitch and Discord. But yeah, if you guys can you guys hear me? Maybe type in the chat. There's a chat on the right. There's like a left. You can hear me, Akash. Thank you, dude. All right, dude. Dope. You hear my soundboard too? Yes. Okay. Cool. All right. Well, that's good. Well, props to Soros with making a good platform. That's pretty easy to use. Then, usually when I do things on Twitch, like OBS like screws up, and I have to spend like 10 minutes like trying to figure out like what's wrong. Hey Ash, what's going on? Good to see you. Nice. Joseph here, Cash here. Nice. Okay, cool. 17 people. Sweet. I'll give everyone like 5 minutes to like, queue in. We're technically 1 minute early. Before we'll start on the AP Physics. Dead. My dead name. Sorry, what's your dead name? Your real name. I hope that's a typo. I hope you don't have a dead name. You guys are too young to have dead names. Wait, is that interesting? Do you guys call like your real name your dead name, or is that just a typo? I'm curious, Ash. I'm always trying to like figure out what the lingo is with the youth these days. A lot of people say their dead name. I've also heard like your government name. That's the other one I've heard. Like she called me by my government or something. Whatever I hear in the rap stuff these days. 19. Sweet. Wow. A lot of you guys are on time. That's super awesome. Yeah, we love that, dude.
That's dope.
Yeah, we're super hyped with that. On time is great. If you're on time to things in life, you'll do very well in life. Actually, a lot of times in life, you just have to show up, honestly. So the fact that all you guys are showing up here is already, you guys are already making like a great first step towards doing well in this AP exam. It's Saturday. Happy Saturday, everyone. Anyone do anything super fun today for Saturday already? It's the weekend. Besides, I guess, studying for this AP exam coming up. You slept for 8 hours. Okay. Nice. I think I slept for like 6 last night. I try to sleep for more. I think as you get older, you sleep like less. Is that how that works? I'm not the biologist person. I mainly do physics and math, but slept 14. Wow. 14 hours. Joseph slept 4. Okay. On accident? How do you accidentally sleep 14 hours? I mean, if you take sleeping pills, you could accidentally sleep 14 hours, but like, I hope not. Yeah. No alarms. Okay, cool. Yeah, it's interesting. I honestly don't even need alarms anymore. My body just always wakes up at some hour. It's just always like, it's like 9 or 10 o'clock in the morning. It's like, you should be up by now. I'm like, okay, I guess so. 30 listeners watching. Wow. Okay, cool. All right. We'll start it in 3 minutes. 3 minutes here. We'll start it. I know you guys are anxious to get into this. I downloaded this actually a couple days ago, and I was like, wow, when I took the AP Physics exam back when it was like AP Physics, it was like AB and like BC or something, but that was probably 15, 16, 17 years ago. So it's super cool that now they have an algebra based one, which is interesting. Oh, thank you, Michael. Yeah, dude.
That's dope.
Yeah, thanks for the thanks. I always like the thanks. Gratitude is great. But yeah. So anyways, a little bit about myself. My name's Dr. Gold. I run a nonprofit where we teach kids for free, mainly on Discord and Twitch. But my friend Soros here, who founded Lighthall, this program that all you guys are on, reached out to me and said, I got this awesome platform where you can teach live to more than just a couple people. Because on Twitch and Discord, I can really only teach to like 2 or 3 or 4 at a time before, and there's like latency and whatnot. But this platform Soros has built, as I can see, like, this is cool. The chat's like just live. Like, I can interact with you guys a lot quicker and a lot more of you guys at once. So we're trying this out. And the AP exam's coming up. So I thought this was a great opportunity because, myself, I've been teaching privately physics, math, any science class, really, math or science. I even do some English, for the last 14 years. And so I have a lot of experience in doing this stuff. And what I always notice on, at least when you're studying for the AP exam, is like the multiple choice is like, whatever, like you can figure that out. It's not that difficult. And there's multiple, it's still like a guessing game at some point. You can still like eliminate choices and get to like the best two and you're good. Yeah, sources in the chat. So yeah, if you guys have any questions or you need help, message him. He'll help you out with stuff. I know a lot of you guys are new to this platform, probably. A lot of you maybe saw my ads on TikTok, or you saw we did some advertising in our Discord, or we sent out a whole email list. So Lighthall's what we're hosting through right now. And then the other company I work with is called Kudu, which some of you guys may have come from. And Kudu is a like an online textbook replacement startup that they created this whole AP1 physics course with a bunch of sample questions and whatnot. And cool. There's some cool review videos that from another guy that we've partnered with. Maybe you guys have heard of him, Jonathan from Flipping Physics. Here, I'll show you guys. Probably see it. Oh, I see it. Okay, one sec. I gotta change my screen sharing to not just that tab. Let's see, window, and I want to. There we go. Share this window. Cool. All right, here we go. Yeah, this is the other guy that we'll show this later in the lesson. But this guy, Flipping Physics, Jonathan, he had 101,000 subscribers. It's pretty crazy. Wow, pretty awesome guy. But he's made also a series of like review videos to study for the AP1 physics exam, and we use a lot of his videos in our review course. So we'll drop links to everything. You can check them out. But anyways, it's 2:05, so let's get started. So what I'm here to do is to walk through. Yeah, Akash says I like that guy. Cool. Yeah, no, he's pretty cool. And he may actually join here on Lighthall at later dates to do some live teaching and whatnot. We pitched him on the idea, and like depending how well this goes, we could work towards that as well. But anyways, let's get started. We're gonna go through the AP1 AP Physics 1 free response questions. There's a PDF that was in the class, I think, that you could download if you want to follow along. You can just watch the stream as we go through this. And what we're gonna do is we're gonna go through the free response questions and show you how to do them. If you have any questions along the way, if anything doesn't make sense, you're like, wait, I'm confused, like I don't get that, whatnot, please use the chat. Chat there is on the right, and you can just type whatever, and I'll be able to see it. I have a gazillion monitors in this system, so I'll be able to teach and also see like what you guys are saying. So if anything doesn't make any sense or you want some clarification on stuff, this is like the time to make sure that we do love it when dudes have a million monitors. I do have I've bought many monitors. I look like I should be like someone in like stock trading or something, but no. But yeah, if you have any questions along the way or something doesn't make sense, and also I'll start asking you guys questions. I'll be like, what do you think this is? Please, like, this is more fun when you interact. And also you learn a lot more when you interact and you do things. If you're just sitting there listening and reading, like, it's like, yeah, you'll get it, but you do a lot more by doing. Yes, if you have to leave early, can you access the stream? I think so. I think you just click on the link, it just goes back. Also, if you have to leave early, I have this set for an hour. That's not set in stone. I can go a little bit over. I got a wedding I got to go to in like 2 hours or something, but like, we can go a little bit further depending, also like in teaching, like something I've learned, like you really don't want to like sit down in front of something for really more than an hour. Otherwise it starts becoming like kind of boring. You're like, eh. But yes, all of these lessons are going to be recorded. So we'll have recordings of them that you can watch afterwards if you want to go through more slowly or something and see what we're doing. I remind you of Vsauce. That's cool. I don't know who Vsauce is, but I take the compliment. I take the compliment, I guess. Okay, nice. Okay, cool. All right. So what we have here is the AP Physics 1 algebra-based free response questions, and what we're going to be going through are the questions they have. So when you get the test, like when you sit down, this is what they're going to literally give you. They're going to give you like this packet and whatnot. And the first question you're going to come to is some nice like table information. I'll refer back to this And this will help you out with like, you know, I'll show you like, well, you could use the formula from this sheet or whatnot, or like, that's actually really nice. They tell you all the trig identities. You really should know these. I'll just give you like a little hint. Like when you go to college and whatnot, they're not going to be nice. They're not going to give you this. So like you really want to actually know how to do these. But that's nice that they still give them to you. Oh, he's a YouTuber. Cool. Yeah. I got to look up all the YouTube people. I'm not really big on YouTube yet. I do a lot of just Twitch at this point. Okay, and then cool. And then they have an equation sheet. This is also very cool. I remember when I was in high school, we had this printed on a t-shirt, and we were allowed to wear that t-shirt to like our tests and whatnot. So we'd be like staring down, like trying to like see like, wait, kinetic energy is what, you know, but I'll also refer back to this. I'll go through like which equations we're using from the equation sheet so you can kind of see. Because a lot of this, that's nice. They at least tell you all the words for it too, which is good. A lot of times they'll just give you this and you're like, wait a minute, what is F parallel? Okay, but cool. All right, let's start it off with the first question here, which is from Kinematics, right? Kinematics, the study of things that are moving, or I like to say just like the study of like throwing balls in the air, just like seeing what happens. Okay, so the first thing here, they give you a nice little diagram. That's nice. And the question says, a stunt cyclist builds a ramp that will allow him to coast down the ramp and jump over several parked cars as shown below. Wow, that's risky. To test the ramp, the cyclist starts from rest at top of the ramp and leaves the ramp and jumps over 6 cars and lands on a second ramp. I'm glad he has the confidence to at least know he can jump over 6. You know, like that's good. But cool. All right, they give you a bunch of variables here. When they do this, these are usually variables that we're going to need to use for our answer. So it's good to like, you know, read through them and whatnot. Also, this exam is timed, so like you want to come. I'll give you guys some tips along the way on like quick ways to recognize things real quick, so you're not like wasting time on the question. All right, cool. They say derive an expression for x naught in terms of h naught, theta naught, m naught. Okay. So the first thing I'm gonna do, I'm gonna look and be like, wait, what is x naught? Like, what are they even referring to? And the nice thing is they tell you up here, x naught is the horizontal distance traveled while the cyclist and the bicycle are in the air. And they even like, they give you a diagram, which is nice too. So x naught is going to be this distance right here. And what they want to know is how far is this person going to travel if they start at a certain height here, h naught, and then they depart, and the angle, and then the ramp has an angle that's equal to theta naught. Okay, so the first thing I do when I see this type of question, I try to put this into like a box of like, what are we doing? Is this like, am I doing magnetism? Am I doing springs? Am I like, this to me is simple kinematics, and it's two-dimensional kinematics because we're dealing with something going up and also going to the left and the right. So I know that what I'm going to need to do eventually is break stuff up into components in terms of x, and y, and we'll get into that in a bit. Okay. So the first thing I want to know is I want to know the distance x naught that this person is going to travel. Okay. So I like to kind of work backwards from these types of things where I'm like, okay, I need to know how far they're going to travel. What's an equation that relates how far something travels, at least in the horizontal direction or in any direction, really? And what you can do, you can go to your equation sheet here and you can see that, this one, right? This is one that relates distance, right? X and x naught with a, yeah, constant. Yes. X equals VT. Yes. Constant acceleration questions. Yes. Yes. Yeah. Perfect, guys. Yeah. And yeah, that's the key thing here. So I know that X is equal to X naught plus V naught T plus 1/2 AT squared. That's the biggest kinematics equation you're always going to use. But in terms of something going to the right, moving horizontally, this is a special situation where the acceleration in this direction is going to be 0. So we don't need to even like deal with this. And right, Akash, you said this is the easy with a simpler form of the equation where you just have x is equal to vt. And really what it is it's delta x is what it is. You really have delta x, which is the same thing as x minus x naught is equal to, we're going to say v naught x times t, because specifically the distance that it travels in the x direction is going to be the velocity in the x direction times the amount of time that it's in the air. Okay. And this x minus x naught, right, which is the distance it travels, that's just what big X naught is here. So I can write that out real quick. I can say that, okay, cool. So this distance I'm trying to get, x naught, is going to equal to v naught x times t. All right. Now, that means we need to figure out two things, right? I need to figure out what v naught x is, and I need to figure out what t is. T is the amount of time he's in the air. V naught x is the velocity in the x direction when he leaves this point in the ramp. Okay. Now let's work on v naught x first, which is we're trying to figure out what's the velocity of this bicycle dude as he's like coming down the ramp right when he leaves the ramp point, and what's that velocity in the x direction. The way to get that goes back to another concept we know, which is conservation of energy. Okay. Does anyone know what conservation of energy is? Like, what do you guys like? How would you describe conservation of energy? What types of energies are there? Energy is conserved. Great. Good. It's kinetic, potential, kinetic, gravitational. Nice. Yes. Mechanical energy stays the same. Potential spring. Yeah, that's springs energy is another one. Yeah. So luckily we don't have any springs here, so we don't got to deal with that. And luckily, this is another important thing. The energy here is only conserved as long as there are no, what they say, non-conservative forces. And really what that is just fancy words for like, make sure there's no friction. Make sure there's no like external things like screwing things up. Yeah, no thermal, right? Yeah, thermal energy is an energy, but luckily that's outside the scope of this question. You guys aren't going to deal with thermal energy. So yeah, good. So in terms of energy being conserved and it's being a simple system, there's no friction and whatnot. What we know is that the total energy here has to equal the total energy here. Okay. I don't think you ever deal with thermal energy in AP1. That's like a thermo. Yeah. Or you guys did? Well, we'll see if we come up to it in a question. Like I'll go through it. But I don't think you guys do thermo. Yeah. So anyways, total energy. So in the simple situation of no friction, no springs, no crazy shit going on, you know, you have two types of energy, which is what we call gravitational potential energy and kinetic energy. Gravitational potential energy is equal to mgh. Kinetic energy is equal to 1/2 mv squared. Okay. So the total energy when this guy is at the top, which did they say starts from rest? I hope they say that. Oh, good. They say starts from rest. Very good. Yeah. Okay. So if this bicyclist starts at rest here at the top, what does that mean about the total energy? What is it going to be equal to? mgh naught. Very good job, guys. Yes, exactly. This is just going to equal to mgh naught. It's mgh, but then h is just h naught, right? That's how tall he is. Yeah, good. There's no kinetic energy because he's starting at rest, so kinetic energy is 0. Okay, cool. That's the total energy there. Then we get to here, right? And so what's the total energy when he's at this point? I do have a soundboard for fun stuff. I do a lot of Twitch, and I know you guys love soundboards on Twitch. You know, it's just like perfect. Okay, yeah. So yes, 1/2 mv squared. Paige, you're correct. Yes. So at this point, right, you technically do have mgh plus 1/2 mv squared. The difference here is though, like at this point, we're measuring height from this point right here. When we say that the height of this thing, right, the energy is mgh, you got to always define where you're measuring h from. If I say that the energy here is mgh naught, that means I measured my height from this point because this distance here is h naught. Good. So at this point, if we're measuring from here, the height is 0 because he's at the same point that we measured h naught from. So that's why this whole term here is going to go to 0, and we don't even have it. So now what we have is just 1/2 mv squared, and that's the velocity here. So this is very cool because now we can figure out what the velocity is of this guy as he leaves the ramp based on how high he was. Okay, or how high in the ramp he was. Let me get rid of this stuff so we can have some space. So I know that mgh naught is going to be equal to 1/2 m, and then let's call this like v. We can call it v naught squared. That's fine. Let's just call it v naught squared. Where I'm going to refer to this as like. Or actually, you know what? Nah, I like using letters. Let's numbers. Let's call this V1, right? I always like to label like the points in time by different things. I'm gonna call this like time 0. I'm gonna call this like time 1. I'm gonna call this like time 2. Okay. So, and you'll see that when I put the numbers underneath. The numbers refer to what is the velocity at like what time point. So when I say V1, we're talking about the velocity at V1. This is also something you, as a general strat, you want to keep like things straight with like what time am I referring to when I say like V1 or V2 or something. So anyways, 1/2 mv1 squared. Okay, so that means that v1 squared is equal to, so you can multiply both sides by 2. You can cancel out the m's. We don't need the m's anymore. So v1 squared is just going to be equal to gh naught. V0? Oh, interesting. Yeah, I want to, Michael, where are you from? Where are you? Are you from the US? Are you from Europe? Jersey. Jersey. Jersey is a great place. Yeah. Interesting. They say V0. Jersey. Yeah. I know for some, I'm from LA, but I went to school in Texas, and like everyone always said not, but like, you know, V0, we can call it V0 too, whatever you guys want to call it. So anyways, v1 squared is equal to 2gh h naught, right? And then I need to square root this thing, right? So I get that v1 is equal to the square root of 2gh naught. Awesome. Okay, cool. So now we got the velocity of this thing. However, that velocity is the velocity in both the x and the y direction, because whenever we do this 1/2 mv squared and mgh and whatnot, we're referring to what's called like the total velocity. And velocity, as you remember, has a magnitude and a direction. So this like v1 we're speaking about is technically pointing in this direction, okay? Which is not exactly what we want, right? Because what we really want is we want v naught x, okay? So in order to figure out v naught x, what we have to do is and you're going to do this all the time in AP Physics, is you need to break up this velocity into components. And specifically, we just want the components such that we have the velocity only in the x direction, and then we have the velocity only in the y direction. Okay. So I'm gonna draw a little triangle. This is why, like, I say like trig never leaves you, or like all this. I used to hate like trig when I was your age. And like anytime I saw like sine and cosine, I'd get like scared. I'd be like, run, get out of there. No. But you use it all the time. Okay. So if this is going to be equal to v1, and then this right here is going to be equal to theta. This is also another like kind of geometry trick that we got to remember, is that they're saying that theta, for instance, is the angle from the horizontal, right? And they measure it like this. But if you remember from geometry, which is like, you know, I don't know, really far back, but you still got to remember it. If you have two parallel lines and they get cut by what's called like a transversal, which would be like this, then what we say is like the alternate interior angles are the same. So this angle is also the same as this angle. Little blast of the past from geometry. So yeah, so I can also call this angle just theta naught. Okay. So this is going to end up being v1x, is what we're going to say. And this is going to be v1y. And also, let me get rid of this. Let me call this v1x, because that's what we're looking for. Not the conservation of angular momentum. Oh, God. Yeah, what is that? 1/2 mr squared or something? Okay, cool. Does anyone know how to get v1x and v1y here? Let me make this got to look better. Sine and cosine angle. Good, very good. Yeah. So like which one is sine and which one is cosine? Sine is vertical. Very good.
Nice.
Sine is opposite of hypotenuse. That's another good thing to know. Yeah. Yeah. If you ever forget like which one, because honestly, depending what angle they give you, it's not always going to be the vertical or the horizontal. If they've given you, I don't know, like this angle, for instance, like it'd be something else. But yeah, if this is the angle we're looking at and this is the opposite, then this is going to be the adjacent. So sine of theta 0 is equal to opposite over hypotenuse. So that's going to be v1y over v1. You can move v1 over, and you just get v1 is equal to v1y sine theta 0. Okay, so that's where that comes from. So this is going to be equal to v1 sine theta 0, and this is going to be equal to v1 cosine theta 0. Okay, I'll take my medal now. Yeah, do you want some claps? I'll do some claps. I invented the SOHCAHTOA. Dude, some teacher got in trouble in California for. I'll show the YouTube video later for like dancing like racistly to SOHCAHTOA. I was like, what? SOHCAHTOA. Anyways, great. Okay, cool. So good. Now we've gotten v1x is what we've gotten, right? That's what we figured out. So the next thing we need to do is figure out time. Okay, so this is where like you got to come like way back and be like, wait a minute, what was I actually doing? So what I'm doing is trying to find the distance that he travels. So I need the velocity in the x direction, and I need the time that he's in the air. Okay, this is always like the cool thing with kinematics is that the amount of time that something spends in the air in the x direction is the same amount of time it spends in the air in the y direction. Okay. So what we need to do is figure out how long this guy on his bike with a death wish is in the air. And the way to do that is to now, and this is what you'll do. You'll do things in one direction like the x direction, and then you I'll show it to you, Michael. It's funny. You do things in the x direction, and then you use that to also do things in the y direction to like figure out like the connecting things. So what I know when this bicycle is going when this bicyclist, right, is going up and then going down, okay, is that the amount of time that he's in the air is the amount of time it takes for him to start at basically height is equal to 0 and then end at height is equal to 0. That's what that's a situation we can use. You could also do something where like we can figure out how much time it takes for the velocity in the y direction to be equal to 0. That's another quick trick you can do. That only works if you're starting and ending at the same height. So I'm going to do this way just for safety's sake. Okay. So what I can now do is I can use that Kinematics equation we did, but I can do it for stuff in the y direction, and that is that y is equal to y naught plus v naught y t plus 1/2 a y t squared. Okay, it's the same equation as we had here. All we're doing is we're just switching the directions. Instead of doing stuff in the x direction, we're doing stuff in the y direction. Okay, so y here's the final height. I want to know the final height is going to be 0, right? Because that's when he hits the ramp, hopefully. And y naught is the starting height. That's also going to be 0. And then what we have here is v naught y. So I need to know the velocity that he's traveling up in the y direction. Luckily, I already figured that out. That's right here. That's just going to be v1 sine theta 1. So that's plus v1 sine theta 1 times t. And then we have, and I know I said v naught here means like the initial velocity, and here the initial velocity when he leaves the ramp is the same thing as v1. That's where that comes from. And then we're going to do plus 1/2. Oh, here's a good question. Is there acceleration in the y direction? Good. Yeah. And that's gravity. Gravity. Very good, Dirash. Very good, Akash. Yep. So that's going to be minus, and gravity is always minus 9.8 and then t squared. You'll probably like, because you do this so much, like I'll just straight up just always write this as like minus 4.9. It's just like, it's a handy trick that, you know, a little shortcut that you'll end up doing. Perfect. Yeah. Good. Yeah. Tor. Very good. Yeah. That's the final answer. But we'll get to that. Okay. Good. All right. So you can solve here for t, right? And so we have, if I move everything over, right, I have that, what is this? T squared, 4.9 t squared minus v1 sine theta 1 t equal to 0. So you can pull out a t here, right? So this is factoring. I could use the quadratic equation here, but like that would be messy. So I'm just gonna factor out a t here. So I'm gonna say that t is equal t times 4.9 t minus v1 sine theta is also equal to 0, right? And so we'll see that this statement is true, right? When t is equal to 0, which that's what we call a trivial solution. Trivial means like, I don't care. Like what? Of course he's on the ground when time equals 0. But the other time, right, is when this is equal to 0. So I say like 4.9 t minus v1 sine theta is equal to 0. And so what was this? T is equal to v1 sine theta all over 4.9. Okay. Or we could say g over 2. Actually, do they say I have to use g? Oh, physical constant. Yeah. Okay. So sorry, my bad. So this I have to use. We can't say 4.9. We have to say g over 2, which if you're dividing fractions, that's the same thing as putting the 2 on top. So we're going to do that. Okay. All right, cool. So now we found our time. And so this is the time. And where's our velocity? This was our velocity, right? So we're going to get x naught is equal to where's V naught? V1 cosine theta times 2 V1 sine theta all over G. Okay. Okay. Cool. And now the other thing we have to use is what we figured out for V1, right? Which V1 was this, right? Which was the square root of 2G H naught. So actually, I think that those are all going to cancel though, right? Yeah, this is kind of cool. Okay, so look. So I have a V1 here, right? I got V1. I got V1. So if I simplify this, V1 times V1 is V1 squared. We'll put the 2. So I got 2 V1 squared cosine theta sine theta all over G. And then V1 was equal, well, this is cool. V1 squared was just equal to 2GH naught, right? Because V1 is the square root of 2GH naught. We square it. So I'm going to get 2 times 2GH naught cosine theta sine theta all over G. And then there's some nice canceling that can also happen here, right? So we get rid of this. We get rid of this. Sorry, this G. And we get our final answer, which is going to be 4 H naught cosine theta naught, technically is what they call it, sine theta naught. Which, let me check, is that the right answer? Yes. We did it. We did part A, which that whole part is worth 3 points. I did that pretty slowly. You guys can tell me in the chat if you want me to speed up. I can speed up. Like I can do this in like 2 seconds, but I like to like start slowly just to like get the concepts out and whatnot so that you guys can see the process and like the equations we use. And then once we've understood that, we can just go through. So yeah, you would need to do this a lot faster on the exam, but I wanted to take time to explain it to you so you could see how everything works. But yeah, good. So that's the distance for the first part here, which is the expression for x naught in terms of all that. Okay, cool. All right, let's see. What's the next part they have here? Okay. So now they say if the vertical distance between the top of the ramp and the launch point were 2h naught instead of h naught with no other changes to the ramp. So this means that our dude over here is now deciding to like be like, I don't know, I want to get even higher. I want to go way up here and like drop in. So they're going to ask, I'm guessing like, what's the maximum distance that he can travel? Right, yeah, here. What's the maximum number of cars he could jump over? So if we go back to our equation that we figured out, right, which was this. So this was x naught is equal to all this stuff. Really nice and big. Okay, cool. What happens to x naught if h naught doubles? Good. Yep. So this is what's called, guys, a direct linear relationship, which is big fancy words for like if this goes up by a certain amount, this is also going to go up by a certain amount, because we're only changing this. The other way to think of this is like call this like, is that an H? It was an H at one point, but here we'll make it better. We can make it stronger. There we go. H naught. Yes. Because there's no roots or divisions or squares. Exactly. Good. Yeah. If this was h naught squared, this is a good question because some things will go as the square. If this was h naught squared and I doubled this, what would happen to x? What would happen to x naught? Good. Goes up by 4. Very good. You guys get that. Awesome. Okay. Oh, here's another one. If it was a square root of this and it went up by 16, how much would it go up by? Also 4. Good. Yeah. Good guys. Yeah. Always good to understand that. Okay. So yeah, this is easy. This doubles. Okay. And in part A, the guy jumped over 6 cars. So how many cars can he do now? This is going to be 12 cars. Easy. You know. So perfect. This is not too bad. Okay. Sketch a graph of the vertical component of the stunt cyclist velocity as a function of the time from immediately when he leaves the ramp to before the cyclist lands on the ramp. Oh, the vertical component. Okay. Well. You guys should know this from kinematics, right? His velocity is going to start as something high, right? He's going to start with a really high initial velocity, right? That's the v1 sine theta, and then he's going to end with negative v1 sine theta, because this is the whole thing. Like whatever goes up has to go down, right? So if he starts with this velocity going up, and then he comes back down. The velocity that he starts going, and this is also very important. This only happens if the height he starts is the same as the height he ends. Sometimes they'll try to trick you on like this stuff, and they'll do something where like he starts here and then he ends up down here, and it's just like, you know, he falls. That's different. The velocity that he starts here is not going to equal the velocity that he ends here. In fact, the velocity here is going to be a lot bigger than the velocity here. The velocity going up here would be the same as the velocity going down at this point because they're at the same height. And that all goes back to the 1/2 mv squared in MGH. The longer I need a soundboard. Yeah, actually, this isn't even that fancy of a soundboard. Well, okay, sorry, I'm gonna hit stuff. It's literally just a MIDI keyboard, and I run it through Ableton. Is what I do. I do music production as well, so I have all sorts of audio stuff I do. Anyways, so yeah, and right, so the velocity is going to start here. It's going to end here. Here's a good question: Is the line that connects the starting velocity and the final velocity? There are three options, right? We could either have a straight line, we could have what's called a concave down curved line, or we could do a concave up curved line. Which one is it going to be? And you got to tell me why. Straight. Good. Why is it straight? Constant. So acceleration is not 0. Yes, good. It's a constant change. Yeah, good. There's a constant acceleration, and that the constant acceleration, right, is equal to g. So what we could say here is, let's say this was like y, and this is like x, right? Delta y over delta x, right, which is the slope of this line, that would be equal to minus g. And where that comes from is that the change in velocity over the change in time, because really the y-axis is velocity, the x-axis is time, that's equal to acceleration. And the acceleration of something going ups and downs, up and down, is always going to be minus g. Yeah, all good. Nice. Okay, so yeah, that's me straight. And then yeah, you need whatever the name. I think this was like square root of 2 GH naught. Is that what it was? Yeah, great, cool. So square root of 2 GH naught sine theta, done. You see, all these other parts are actually quite easy. Like once you've done the first part, everything else is just like figuring out stuff. Yeah, cool. All right, that is question 1. Does that make sense for everyone? Anyone have any like little last minute like questions about kinematic stuff like that before we head into, what is it, round 2? Okay, nice. All right, here we go. All right, now we're dealing with springs. Okay, this is very interesting. It's like I always get like annoyed when I see so many words. I'm like, why are there so many words in this question? But okay. A group of students is investigating how the thickness of a plastic rod affects the maximum force in which a rod can be pulled without breaking. Okay, so they got like probably like a spring or something, or I don't know. Have you guys done this with they do this like crackers or something, like pull on crackers and then it splits, you know? Anyways, okay, they're discussing models to represent how FMAX depends on the rod thickness. Okay, so what they're doing is they're trying to figure out what maximum force can I exert on this rod before it breaks, and how does that depend on the thickness of it? One of the students here, student A, says that, oh, FMAX must be directly proportional to the radius of the rod. Whereas student B here says it must be directly proportional to the cross-sectional area of the rod, which is the area of the base shaded in the figure above. Okay, cool. That's a really small photo, but okay, cool. Yeah. So basically what they're saying is that, like, cool, I got my rod right here, and they want to know whether the force that it takes to break it is directly proportional to what we say is the radius. This would be the radius, or whether it's proportional to the cross-sectional area, which would be where's my like paint tool? There we go. Which would be this. This would be equal to the what we say is the area. Which also, it's good to just write this stuff down. You know that the cross-sectional area relates to the radius, right? That's equal to pi r squared for a circle. Okay. So, all right, cool. Students have many rods. The rods are all the same length, blah, 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 6 different thicknesses. Design an experiment procedure to determine which student's model correctly depends on the rod thickness. Okay. Okay. Well, it's interesting. It's cool. This is like an experimental design question. Very unique, but a good thing to know, especially if you guys want to do physics later in like college or like grad school. You have to know to be like, I have a problem. I have a question. How do I solve it? Like, how do I figure this out? This is a good way to kind of get practice with that. So one thing we need to do, if we're making claims about FMAX refers to the maximum force you can stretch this thing before it breaks. That's probably something we need to measure. Okay, so I would say that the max force before it breaks. Okay. The symbol for that quantity, they kind of give it to you, right? That's just FMAX. And then equipment for measure. That's cool. How do you measure? You can measure forces in a number of ways. You can use weights. Like we could hang this thing and just put weights on it and just keep putting weights until the thing snaps. The other way I think is what do they call this thing? It's like a force meter or something. One sec. There's a special name for this thing. A force probe, a force sensor. Cool. All right, awesome. Yeah, good. All right, cool. We'll call it like a force sensor. I think that's cool. You guys have those before. You've had those. I think here's like a picture of one. Here, I'll get one real quick. Force sensor. Oh yeah, these are cool. You know they also do these for like your luggage. You see like luggage weight scale thing. You guys seen these before? Yeah, this is a pretty basic one, right? Like one of these things. Damn, this thing's ancient, dude. This thing's older than me. But yeah, one of these would also be a way to measure the force on something. Okay. All right, cool. That's something we definitely need to know. And then we're trying to relate this, right, to whether it's dependent on the radius or the cross-sectional area of the rod. So we probably need to measure both of those things. The nice thing is that, like, in order to measure the cross-sectional area, we just need to know the radius because we can do math to, like, figure out that. And so, yeah, and then radius is radius. So the quantity to measure is going to be the radius of the rod. Symbol for that is R. Equivalent, you use a ruler, or calipers. If you really want to get fancy, calipers are cool. Does anyone know what calipers are? I asked some kids in my Discord this the other day. Car part. Ha! Close. Here, I'll show you guys because this is useful to know for later in life. You're right. So calipers on brakes are definitely a car part, but yes, calipers, these are what calipers are. They're like super precise, like rulers is what they are. Like you can use these, and instead of like going to a ruler and being like, oh man, dude, is that a quarter of an inch or an eighth of an inch? Vice grips do look similar, Michael. But this is like vice grips with like a little calculator thing on it, which tells you exactly, like down to like a lot of decimal places, how big something is. So this is probably what you would use. You can see this someone's actually like literally using it to measure the thickness of a rod. That's how that works. Okay, cool. So ruler, or if you want to get fancy, like get some style points, be like, yeah, dude, calipers, Okay. Awesome. All right, that's it. That's it for part A. Wow, okay, whatever. All right. Let's see part B here. Describe the overall procedure to be used. Provide enough detail to replicate the experiment. Any steps necessary? Okay, I would like. This is, I don't know. This is kind of silly. I mean, I don't know how much. If you guys really need help with this, you can tell me. But like, I would say just like measure the radius of the rods. Pull on rod until it breaks, and note the force that it breaks. Right. Apparently how many points is that worth? It's worth 4 points. No. That whole thing's worth 4 points. Okay, cool. All right. I worked in a mechanics shop. This only thing. Hey, it's cool to work in a mechanics shop. I did experimental physics in grad school, so I did a lot of like tinkering with my hands and like how many are from Discord? Dr. Gold's actual Discord. Yeah, if you're from my Discord community, say hi or something. Say hi. Be like, what's up? Soros, yes, you are on my Discord. I'm torn between studying physics and nursing. Well, how old are you, Michael? Like, that's always the question. You got a lot of time. 17. Oh, dude, you got so much time, bro. Like, you got like 4 or 5 years before you figure out what you actually want to do. You can do both. And actually, in order to you can try doing both, along the way. Because a lot of like nursing degrees require you to take physics anyways. That's it. I'm the only one. Yeah, it looks like you're the only one that yeah. My sister's a nurse. I think 3 of my sisters are nurses. I'm the physics guy, so Okay. For Yes, yeah, thanks guys. Yeah. If for all y'all that are watching, I do this on Twitch 4 days a week, and like you guys can ask whatever. You can ask anything. Like and I help you guys out for free. There's a Discord link that Source posted. And we have like incentives. I give out gift cards and rewards and stuff, tons of stuff, like just for asking questions. Thank you, Source. You're amazing too. Okay, so here we go. For a rod of radius R0, it is determined that FMAX is F0 as indicated on the graph below. Okay, great, awesome. Okay, on the grid, clearly label each graph. Oh, okay. Oh, the appropriate model. Okay. So model. Okay, we got to go back and be like, what the hell is model A? Okay. A claims that Fmax is directly proportional to the radius of the rod. Okay, cool. This is radius and this is force, right? Yeah, nice, Michael, dude. Directly proportional means that it would just be a straight line. Be like here. That's what something's directly proportional. Like y equals to mx plus b. That's a straight line. That's where x is directly proportional to y by the factor of m. Okay. That's what student A says. And then if we go to student B, directly proportional to the cross-sectional area. That's different, right? Because what's the equation for cross-sectional area, guys? Who knows it? Pi r squared. Nice. Michael says, I win. No. But you get style points for trying there, dude. Yeah, it's good, Matthew. Pi r squared. Very good. So if the force is proportional, that's what this squiggly thing here, like looks like the goldfish or something, is proportional to pi r squared, right? That means that this is something that looks like y is equal to x squared, basically. And if we remember from way old math classes, right, y equals x squared looks something like this. It's like a u, right? Where this would be like x is equal to 0, right? So that means it's curved, right? So if this one is going to be equal to a, then the one that's curved, which is B, is going to look something like that. That's going to be B. Okay. Cool. All right, let's see what else they tell us. All right, that's part B. Nice. We're moving along, moving and grooving. Measurement taken by a group. Cool. Okay, so now we got points. That's cool. We got points. Okay. So then now they want us to graph. Great. Okay. So let's remember, right, that what we're doing is you're always graphing like y versus x, and in this case we were saying that the maximum force was proportional, so we're graphing that versus the radius. Okay, so I'm gonna just label my axes right now, just like R0 and F max. The nice thing is that on this previous question, they kind of already gave you a hint, right? They already kind of like drew it for you, which was nice. Okay. And now we got to graph it. So when I look at graphing things, I want to look at like what range of values are we looking at. So rod radius, which is R0, which is like in millimeters, right? Always label your axes. Is going to go from 0.5 to 2.5. So let's look how many divisions I have. I have 1, 2, 3, 4, 5. Okay, cool. So I could just probably call this 0, 0.5, 1, 1.5, 2, 2.5, 3. That's pretty decent. You could like, if you really wanted to, like, you could like be like, oh, this is like 0.5 and this is like 1. Don't do that. Like, you don't want to piss off the graders. So like, try to make it like as large and use as much of the space as possible so that like, they can read it. All right, then Fmax, this is interesting. Fmax goes from 40 to 900. Wow. Okay. So I'm going to approximate this as going from basically 0 to 1,000, right? Which if I divide that into 1, 2, 3, 4, like 5 points, what's my interval going to be if I'm going from 0 to 1,000 by 5, by 5 different sections? What good? 200. Yeah, nice, awesome. So 200, 400, 800, or sorry, 600. Can I count to 10 today? 800, and then 1,000. Okay, good, awesome. All right, cool. And then this is also in newtons. I should label that. Okay. All right. So at 0.5, it's equal to 40. So this is 200, and look, we got 1, 2, 3, 4, 5 divisions. It's by 40 then. Okay, so each one of these divisions is 40. That's good to know. So that's going to be there. 1 is going to be at 120. That's nice. So 40, 80, 120. That's going to be right here. 1.5 is going to be at 320. So we're at 200. So 240, 280, 320. We're up here. I can already tell this thing's not going to be linear. And then 2.5 is 900. Like, wait, what? 840, 880, 920. So it's like right here. Okay, cool. So, yeah. The next question is gonna be like, what type of line is this? It's like, it's definitely this one. This one right here. It's this one, because remember, student B is the one that said that FMAX was proportional, the goldfish thing, to R squared, and R squared is a nonlinear curve. So done. Cool. Oh, that's question 2. All right, that was fast. I see. Are these all the same points? That one, how many points was this one? 12 points. What was the other one? 7 points. Wow, they actually ranked 1 as less point. I think 1 would take longer than 2, but okay. That's also like a thing. If you're going through these questions, and you should always do this. Like, when you get your exam, look at your look at the FRQ section and try to pick out which ones you immediately can do very quickly. Like, you're like, it'll either be like, I've already seen this one like 4 times, I already know how to do it, or you may be like, I've never seen this at all. Skip the one where you're like, I've never seen this at all. Like, come to that later. You want to make sure you get as many points as you can, and you do that by like doing the ones you can do first. And the grading scheme depends all the time, but I remember when I took AP Physics, like, if you at least got like a 50, like if you got half the questions right, you still got like a 3 or 4 on the exam. So like, they set the bar kind of low. Maybe it's different for this year, but you want to make sure you get as many of those points as you can. Okay, here we go. A student of mass MS is standing on a smooth surface, uses a stick to push a mass MD. The student exerts a horizontal force of FH. Blah 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 blah. Okay. Assuming the disk begins at rest, determine the expression for the final speed of the disk relative to the surface. Okay, cool. So I always like to draw a picture for things. It's kind of my thing. So we got a student. We got student here. And they're like pushing like the stick. And they're like, come on, please move. And then there's, so this guy's got a mass MS, and then he's pushing a disk here, which we're going to say is mass MD, okay? And he exerts a horizontal force, okay? So that's going to be this way, FH over a time interval. So he does this from T equals 0 to T equals F, or T equals TF, sorry, TF. And there's no friction. Nice. I love that there's no friction. Friction makes everything worse. And what are they asking for? Oh, final speed. Okay, that's what they want. They want final speed. I want this. Okay. Final speed. Okay, cool. 3 and 7 are 2 or 12. Okay, that's cool, Tor. Yeah. Yeah, this one is 12 points as well. Interesting. It's interesting that they make 1 so low. But okay. All right. Cool. So we're trying to get VD, the final speed. What we have is we have a bunch of masses, we have some forces, and we have some time. Okay. What concept, what like equation do you think we're going to use to figure this out? How are we going to figure out this final speed of this disk? Change of momentum. Very good. Yes, Selena. Very good. Very good job. Yeah. If you didn't know that, this is the other cool thing about physics, is that like you can figure it out just on the equation sheet if you really want to. So I know I need like F, I need time, and I need like mass in there maybe at some point, right? So I need like these 3 things, right? What equation has that? You just like go through this and you're like, ooh, okay, here's an F and a T. I like that, right? But what about the M? And you're like, ooh, but delta P, right? That's the same thing as delta. Remember that P is momentum, delta MV, okay? Which is really just M delta V, because mass doesn't change, hopefully. So this will tell you right away what the equation is. Just look at the variables you have, what you're trying to get, and then like, oh, and they do it here, right? P equals MV. Yeah, you can just slam that into there. So that's a useful way if you forget. If you like blank out, I know we all get like test anxiety. We're just like I don't know what to do. Like you can always fall back on the equation sheet, look at the variables, and it'll probably pop up out of it. You'd be like, oh, there's an equation. So yeah, very good. So what we're going to do is change momentum. This is actually called impulse technically. And what it says is that the change in momentum, which is equal to m delta v, is equal to the impulse, which is equal to the average force exerted times the change in time. Okay. So using this equation, I have all my things here, right? So change in time. Remember, delta is always good. Delta t is always going to be equal to was it this tf minus t0? T0 is the initial time. So I have the mass of the disk, right, is md. The change in velocity, so that change in velocity, right, is going to be v final minus v initial. But since this thing starts at rest, right, this is just going to be equal to 0. We don't care about this. And then this is equal to the average force, which I think they give this, right? Average force is FH. That's the... They say it's a constant force, which means it's the average force, right? The average, if something is constant, the average is the same as it. And then this is the change in time, right? Which is TF minus 0, which is just going to be equal to TF. Okay, awesome. So you can then solve for this, and you just get that VF, which is what they're calling the final speed of the disk, VD, is going to equal to the force that's applied times the final time all over the mass of the disk. Which, is that correct? Yes, it is. Nice, cool. All right. Okay, now they say assume there is negligible friction between the student's shoes and the surfaces. Okay, so this dude's like standing on ice or something, you know, and he's pushing a thing. After time TF, the student slides with a speed Vs. Determine an equation for the ratio of Vd over Vs. Express your answer in terms of Ms and Md and all the constants. Okay, cool. So what are we going to use here? We're not going to use change in momentum for this one. What's the other concept we're going to use here? Conservation.
Oh, yes.
Nice, guys. Yes. Okay. Conservation momentum. Again, you can only... all these conservation things only work when there's no friction, no thermal energy being lost, like nice ideal things. And they say that. No friction, which is good. And what that says is that the momentum before... the total momentum, this means total, sigma here. I don't know if you guys have seen that. It means just add up all the momentums. Add up all the momentums of everything in what they call the system. The system is a big fancy word for like what the picture is, like what's happening. All the momentum before has to equal the sum of all the momentum afterwards, okay? So if we look at the before, right? Before, it's just the dude with the disk, right? So momentum, remember, of an object. So we can say like massive momentum of the disk, which is also equal to the momentum of... well, okay, no, we'll get to that later. Momentum of the disk is the mass of the disk times the velocity of the disk, which before he pushes on the disk, this is 0 because everything starts at rest. And the same thing can be said for the momentum of the person, because the velocity of the person is also 0 at the beginning. So the total momentum before, that's equal to 0, okay? Which means that the total momentum afterwards also has to be equal to 0, okay? So afterwards, what we're going to have is we're going to have the mass of the student times the velocity of the student plus the mass of the disk times the velocity of the disk, okay? This all has to equal to 0. And what they're asking for us to solve for is for the ratio VD over VS, okay? So this is just algebra to get VD over VS. What I'm going to do is I'm going to move this like over here. So I'm going to get the MD VD is equal to negative MS VS. And then, you know, divide this side by MD, divide this by MD, and then also divide all this by VS, divide this by VS. And then you get the final thing, which is VD over VS is equal to negative MS over MD. Yes, cool. Does that all make sense, guys, so far? Was any of that confusing? Makes sense. Great. Okay, awesome. If you guys got it. Nice. All right. Assume that the student's mass is greater than the mass of the... okay, so assume MS is much bigger, or is greater than MD. On the grid below, sketch the graphs of both the speeds of visibility. Assume that neither disk nor the collides with anything after T equals TF. On a vertical axis, label VD and VS. Label the graphs S and D for the student and the disk, respectively. Okay, cool. Okay, this is good. So we got to think about there's like two situations here, right? So if it asks for speed, should we let the ratio be positive? Yes, right? Because speed does... the negative is a direction, right? Did they say it's a speed? well, they just said VD over VS. Velocities have directions. So, yeah, if they ask for the speed, absolute value it, just make it positive. If they ask for the velocity, right, you need to include the negative. Okay, this is a little tricky. So let's remember that from 0 to TF, this is where they're like pushing on each other, right? Okay. And then, okay, speeds, interesting. Okay, yeah. So yeah, because what's going to happen here, right, is if because there's a negative here, right, that as this person like pushes on the block, if the block moves this way, this guy's technically got to move this way, right? However, he's going to move that way at a much slower speed than this, because the mass of this is a lot smaller than this. Okay, because right, by the ratio here, right, VD over VS is equal to MS over MD. So if so the velocity of the disk is big, that means that the mass of the disk must be small, and then the mass, well, actually, if the mass of the student is big and the mass of the disk is small, then this whole ratio is very big, which means that the velocity of the disk is much greater than the velocity of the student. That might be confusing. Let me know if that was confusing. Also, like, big thing pushes small thing with a force. Small thing's going to go very fast. Big thing's going to go kind of slow. That's just conservation momentum. But that's only yes, that's happening the entire time. But from 0 to TF, this is important. This is where the person is exerting a force on the disk. And what do we know about what's happening when there's forces involved? What's the equation you guys all know for F? What is F equal to? F equals MA. Yes. Yeah. Get that like tattooed. Don't get a tattoo. But like, yeah, F equals MA, right? So what that means is if there's a force being applied, there is an acceleration. Now, if there's an acceleration being applied, right, what does that also mean? What's changing? The velocity. Very good. Very good. Very good. Okay. So from the time 0 to TF, this speed needs to be changing for both the person and the disk. And we can kind of use like just limiting cases here. Limiting cases means like we just look at like the extremes. Like, so at time equals 0, right, we know that the velocity of both of these things here, I'm going to do this is like student, and let's do this for like disk. Okay. The velocity of both of these things is going to be 0, right? The person and the disk are 0. And then what happens is the person pushes on the disk, and the disk feels the force from the person. So since there's a force being exerted to the right on the disk, and this is the other thing, this is Newton's second law, third law, or something. For every force, there's an equal and opposite force. So if this person pushes with a force F, like this is the student on the disk, then the person receives a force of the disk on the student. Okay. So that's why this guy also moves backwards, why this thing moves forward. But let's also remember that that force is proportional. That force, right, is equal to the mass times the acceleration. So the acceleration is equal to F over M. Okay. So if an equal force is being applied from the person to the disk and from the disk to the person, but the masses are different, that means that the accelerations are going to be different. So the bigger the mass, the slower the acceleration. And acceleration is the change in the speed. So that means the change in the speed for the bigger thing is going to be smaller. And so what we can do is we can draw like, I don't know, like a small line from this, right? Oh, do they want me to actually label this? Oh, no. Yeah, they don't actually give me the M's. Yeah, okay. Whereas the or sorry, wrong thing, wrong color. So yeah, the student's speed is not going to change that much. However, the disk's speed is going to change a lot, right? And that has to do with this concept here. The acceleration is equal to the force over the mass. Okay. All right. After TF, right? TF is TF refers to the time that they're applying the force. After TF, there's no longer force being applied. Like the disk has left the puck, and the two people have separated, and so there's no more force being applied. So if there's no more force being applied, what's going to happen to the speeds? Constant velocity. Nice. Very good job, Lucas. Yes, constant velocity. Yes. So if there's a constant velocity because there's no acceleration anymore because there's no force, this is going to remain the same. And then this is also going to remain the same. Wrong color. Where this, again, this was ED, and this was equal to VS. Great, cool. I think that's all they need you to label. Yes, okay. All right, let's see. That was a 4-parter here. We'll do this last section, and then I'll end for today. Because, yeah, we're not going to start question 4. That would take too long. We can do this real quick. Okay. And these are all word problems, which is kind of nice. I don't think we have to do much math. Okay. They say, oh, so now the disc is flying along its way, and it's about to hit the block. It's about to, just crash right into this thing. And they have some questions about the center of mass of the disc block system. Okay. Center of mass, right, refers to if I were to try to balance this stuff somewhere, what is the point where I would balance it? If something is very heavy and something is very light, the center of mass is going to be skewed towards the heavy, towards the heavy thing. Okay, suppose the mass of the disc is much greater, so this is heavy, than the mass of the block. Estimate the velocity of the center mass of the disc block system. Explain how you arrived at your prediction without, okay. And then what happened? Do they stick? Ah, they do. They do stick. This is cool. So they stick together. What type of collision is this? Do you guys know? Inelastic. Very good. Very good round. Chantus, Lucas. Yes, perfectly inelastic. Yes. Yeah, they stick, right? Cool. Another little bonus question. What is conserved and what is not conserved in inelastic collisions? Momentum is conserved. Kinetic energy is not. Very good. You guys got it. You guys are on top of your shit. You guys are good. All right. So yeah, these two things stick, and they want to say what's the velocity of the center mass system if the disc is much greater than the mass of the block. Okay, so if this thing is really heavy and it hits something that's very light, then what we can do is by conservation of momentum, right? So we can say the mass of the disc times the velocity of the disc, and I think this is at rest, right? Yeah. So plus the mass of the block times the velocity of the block, which that's 0 at the beginning, has to equal the mass of the disc plus the mass of the block, all at what we call, which is the final velocity v final. This is the equation that relates it to. Okay, so if this is really big, if they're saying the mass of the disc is really big, and we look here at calculating the velocity. If this is really big, let's say this number was 1,000 or something, and the mass of the block is tiny and it's 1. Okay, then this mass of the block isn't really going to change this final velocity because this mass of the disc compared to the mass of the block is much bigger, such that we can almost ignore this, is what we can say. And so what our equation would turn into is just mass of the disc times velocity of the disc at the beginning. It's just equal to mass of the disc times the velocity final. And you see how these then would just cancel, right? And so you have the velocity of the disc before it hits and the velocity of the disc block system afterwards. These would just equal each other, right? So this is how we would say it would be VF would just equal V0 is what I would say. What would they say? They would say VCM. It's interesting they say VCM, center of mass. Well, yeah, they're talking about what they're really saying is the velocity of the whole thing together, because and that's interesting. Yeah. They're talking about you have a disc and you have the block, and then they're calling this whole thing CM. Cool. That's a little superfluous. Okay. Suppose the mass of the disc is much less than the mass of the block. So this is a really light thing smashing into a heavy thing, right? What do we think is the velocity of those two things once they collide? Tiny. Correct. It would be deriving it mathematically. Oh, because they don't want you to derive it. Oh, without deriving it mathematically. Okay. Well, that's interesting. Wait, what's wrong with using math? Okay, look, I'm looking at the grading sheet. But the grading sheet says you're allowed to also do it mathematically. But that's kind of silly. It's silly that they say estimate, explain. Yeah. English test, not a math test. You're like, what? What is this? You can put down the math. They're not going to get mad at you. I'm looking at the grading sheet that people put down the math and they were fine. Okay. But yeah, you could also look at this from this point of view, right? So mass of the disk plus mass of the block, right? Times VF. So now the tables have turned, you know, how the turntables. So if the disk is now very small, this is 1 and this is like 1,000,000, then this is insignificant, okay? So now the MB in the VF is going to equal MD VD0, right? But this is also small, right? This is small. So this whole thing also goes to 0. So this is where like the final velocity is basically just going to be 0 as well. Again, where that came from, massive disk, velocity of disk initial equals massive disk plus massive block. If this is small, then this is also small, okay? And if this is like really big, like let's say this is like 1,000 or something, then you can kind of get rid of this and you can kind of also get rid of this. This is in physics. You'll do this a lot in like, what is it? Probably late college and like early grad school. There's a lot of like, you'll see equations and be like, oh, but the answer is really this technically. But then what they do is they start like knocking variables off due to what they call like ordering. Well, they'll be like, well, if this is big and this is small, we can just ignore this. And that's kind of what they're introducing you to here. Is they're introducing you to the concept of in life, everything has like these big equations and whatnot, but you can ignore certain things because they're insignificant. Like they don't matter very much, or they don't affect the answer. Okay. Now suppose that neither objects is greater than the other, but they're not necessarily equal. Derive an expression. So this is literally what we came up with, right? So MD VD. So now they're like, okay, now you can do the math. Is equal to MD plus VB over VF, which they're calling V center of mass, final velocity. So you just move this whole thing over, and you just get that MB VB over MD plus VB is equal to VCM. Is that what they get? Yes. Cool. Consider the scenario where the mass was greater than the mass of the block. Does your equation? Yes. Okay. Oh, this is where you can do the math, right? Yeah. Okay. And this is where you can do the math. Where this is actually kind of cool. So here, I'll show you how this works actually. So this is a cooler way to do it. Wait, let me go back. Where did I put it? No. There you are. Tried to run away from me. And I'll show you algebraically how this works. This will be the last bit, and then I'll let you guys go. All right. So VCM is equal to MB VB over MD plus. Oh, no, sorry, this isn't VB. Sorry, this is. You guys gotta catch me here sometime. This is MB. Even I make mistakes. I make tons of mistakes. A lot more on the weekends. MD plus MB. Okay, cool. So they said, so we're saying that MD is much greater than MB. Okay, so they say the mass of the disk is what we would say is this means much greater than the mass of the block. If you want to show how this works for limiting cases, let's divide both sides by MD here real quick. And so this becomes 1. So 1 is much greater than MB over MD. Or another way to say this is that MB over MD is much less than 1. Or that basically this ratio, MB over MD, is basically equal to 0. Okay? And I'll show you why that's important. Because now here's what I'm going to do. I'm going to divide the top and the bottom both by MD. This is you probably also did this in math when you did asymptotes, like to figure out like what the limits are like at the extremes. Or maybe that's a calculus thing. But so if I divide this all by MD, I get MB BB all over MD, and then I get MB over. And why do they have to use like two symbols that look exactly the same? Wait, one sec. MD over MD. Okay, I should use capital B's. That'll make things easier. Okay. Plus MB over MB. Okay. No. Sorry, we divided by MD. Okay. So now look what happens. So MD over MD, right? This just becomes 1. This is MB over MD, which we said earlier, right? MB over MD is equal to 0. So this goes away to 0, right? And then this is MB over MD, right? This is also equal to 0. So I end up getting 0 over 1, which is just basically 0, or like very small. And that's what we said. We said if the block, if the disk is much heavier than the block, then wait. Much wait, did I do this right? VB, yes. The velocity center mass is 0. Oh no, yeah, 0. Oh, okay. Sorry, I made a mistake here. This is a problem with my D's and B's. Sorry, this is MD. This is what I meant to say. Sorry, this is. I was wondering why like this was looking different. Here we go. Let's forget that last bit that I said. Okay, now I'm going to divide it. MD VD all over MD over MD over MD plus MB over MD. Here we go. Okay. MD over MD is 1, right? This is just VB. All over, this is also 1. This is 0. So I have VB over 1. So here we go. VB, or VD, sorry. Velocity of the center mass is just equal to the velocity of the disk, which, yes, that's what we said earlier. So that's it. All right. My brain's kind of scrambled at this point. That's why you can start telling when I start making mistakes between like B and D, I'm just like, okay, I gotta check it out. Anyways, was that helpful for you guys? Did you guys understand that a little bit more? Yes. Awesome. Cool. Joseph says yes. That's awesome. I mean, yes. Do you guys have any other last minute like questions about things? I'm gonna host 2 more of these sessions because we still got to get through. Looks like question 4 and question 5. Oh, Atwood machines. Wow. Okay, so there's 2 more questions we got to do. So I have 2 more sessions. I'm gonna do another one on Monday at the same time, and then another one on Wednesday because you guys got the exam on Thursday. So if you guys want to, I think if you're signed up, what are some materials that are considered acceptable? Are we talking about this section? Was this the stuff? Or any of these for AP2? Materials that are acceptable, basically anything you could find like in your classroom, or like maybe in like anything that's like, real. Like don't start like pulling stuff from like sci-fi like movies or stuff, rulers, scales and whatnot. Don't say like anti-gravity gun, like, or I don't know, that doesn't really work. Are any of these for AP2? I could do some for AP. So I'm the companies I work with and whatnot, all they've been really focusing on right now is AP1. If you want, Lucas, if you want to get help with AP2 and you have questions, use there's a link to that Discord here. I'll put it in here so you guys can have as well. Here, maybe I'll show you guys a little bit real quick, like what I do on Twitch. I love this Lighthall platform because it's very cool. I can interact with you guys live, a lot of you guys live and whatnot. But here's an example of the Twitch I do. So if you join our Discord, you'll get access to the community and whatnot, and that's where I communicate and say when all the streams are, when everything else is happening and whatnot. But I have a Twitch stream I run on Monday, Tuesday, Wednesday, Thursday at different times. And what happens is you can come live on the Twitch, you can ask a question, and I'll go through it one-on-one with you, just like a private tutor would. And it's all free. I think I was looking up like, all right, I make like cool questions. Like this was someone was asking about like warplanes, and I came up with a physics question to go through it. But yeah, so the Twitch, I'll give you the Twitch for that as well. It's twitch.actual.education. And then the last thing we have is, okay, so if you guys want to practice more on these types of problems, on the multiple choice, at least we have a lot of stuff for the multiple choice. We have a Kudu course set up. I gotta remember what's the it's which one is it? It's a.actual, or it's kudu.actual. No. AP1 kudu.actual. Let me make sure that's right. Yes. Okay. This is it. Yeah. Okay. So I'll show this real quick for you guys that are watching. If you go to AP1 kudu.actual.education, you can sign up for this online course we have where we have tons of multiple choice questions that you can go through. So I already have an account, so I think I can just sign in. Let me sign in real quick. Maybe it'll let me in. This is probably doesn't have that account set up. Maybe it does. Okay, but here's what you can do. You can sign up with real email, fake email, whatever you want. Just put your name and whatnot. This is my personal email. Not an instructor. You're going to hit save. You're going to add course, and then there should be a course here. Where's the course ID? I think if you just type it in again, it'll come up. Here we go. Add course. And there, it's CAS 9VZ. If you just type that link in once you've created an account. And then here's the very cool thing is this is a whole course that we've created for you guys in order to get more practice with AP Physics 1. And it's all broken down into sections here. So here we have the kinematics, dynamics, work, energy, power, all this stuff. You can go into any of these sections. Let's say, for instance, you're like, okay, I really don't like, angular. Someone in the chat here didn't like angular momentum. Who didn't like angular momentum? Someone was like, ooh, I don't like that. You could go in here. You could click rotational dynamics, right? And then what we have here is that there's a YouTube video of this guy flipping physics, Jonathan, who's made these. He's made these. Gravitation hurts your brain sometimes. So here, yeah, let's do some gravitation. So here, you could go to universal gravitation right here, right? And here we have these videos that have been we've been given permission to share with you guys from Jonathan. And he does like this cool like 9-minute tutorial on like what's all the you need to know. And then if you click here into lecture notes, there's also a PDF which is useful for studying because it shows you basically what all the major things you need to know, what the equations are. And then afterwards, you can go through and you can check to make sure you understand everything by going through these questions. So here we have like some pre-lecture questions, which these refer to the video. And once you fill those out, you can also go to the official AP1 physics questions that we've written that are going to be very similar to the multiple choice questions on the exam. What section would have springs? So springs would be in, is that work, energy, and power? Probably work, energy, and power. Let's see. 1/2 mv squared. Yeah, here we go. This has springs in it, right? So work, energy, and power has springs in it. There are some good pre-lecture questions here. And then there's, I hand wrote all these questions into here. Someone else wrote the questions. I transcribed them into this. But yeah, here are a bunch of like AP physics type questions with springs that you can try them out and see whether you get the right answer. And you get unlimited tries. So this is a great like way to just diagnose how you're doing. Anyways, so yeah, that's Kudu. So super cool. That's who I'm working with, partnering with to do this stuff. Any other last questions before we leave? Cool. All right. Well, thank you very much for joining, everyone. Thank you, everyone, for participating, whatnot. We'll have 2 more of these sessions. So tell your friends, if they missed out on this one, they can come to the one on Monday. Also, these will be recorded, so you can share them with your friends, and they can also watch the recordings. And again, there are links to all sorts of other resources there you can use to prepare for the exam. Thank you again, Soresh, for setting me up with this. This is pretty cool. I'll see you guys on Monday, and have a great rest of the weekend.